my name is Rami Khalil. I'm a senior protocol engineer at RISC Zero, and I hope you have an idea of what zero knowledge is. If you don't, and you're only familiar with signatures, a nice example I like to use is with a signature. Basically, you have a private key that you're using to create a signature for a message with respect to the public key. For a zero knowledge proof, you essentially have a program and an input, and you're looking to create a proof for the output. And you don't want to reveal the input, similar to how you don't want to reveal the private key. If you need more information, go to risczero.com, look at all our docs, use our software, set it as your homepage, set it as the homepage of everyone you know. Get in there until you're really good with ZK. We're basically a ZK VM, and what that means is you write programs instead of circuits. So no R1CS constraints, you don't have to worry about that. You write regular Rust programs. You compile them down into RISC-V bytecode. You can also write non-Rust, but our toolchain only supports compilation down from Rust right now, and some C support. That runs in the VM for as long as it needs, and then you get a short proof at the end, no matter how long the execution was. So how does this work in your stack? It's similar to how you would program for Ethereum. In Ethereum, you write a Solidity contract, you boil that down to EVM bytecode, you run transactions against that bytecode, and you get receipts in the end to tell you what happened, and that you can use, you can verify against the Ethereum chain. Similarly with RISC Zero, you better write a Rust program, you compile it down to RISC-V bytecode, and you feed it some input, but you get a cryptographic receipt at the end that's self-contained. You don't need a chain to verify it, it's, the proof is in it. And you also, instead of the EVM, that's using the ZK VM. So it's been a really good year for us this year. We're now on Mainnet, we're in production, we're the fastest general purpose ZK VM out there right now. It's pretty good in terms of proving cost, for example. So one Ethereum block, it is an order of magnitude or two above circuits, but it's feasible to use. Recursion is really fast. It runs on your machine. You don't need a beefy AWS machine to use it. You can prove on your CPU, which is dreadfully slow, but you can also prove locally on your GPU. And if you have a 4090, it's as if you're running like a 500 kilohertz local computer. So how do you get started? You install our RZ-up utility, and that augments your cargo with a few more commands that you can use to instantiate new template projects, compile bytecode or verify proofs. Someone sends them to you. And what exactly is proving? Well, it's taking a program, some inputs, throwing that into the ZK VM, and then getting receipts. And the rest of the talk is mostly going to be about receipts, because receipts basically come in different flavors. And what a receipt is a combination of the output of your program and the cryptographic proof. Now, the receipt flavors are basically a composite receipt, which is like a very big receipt that is just easy and fast to compute, or a succinct receipt, an actually succinct receipt, not a branded receipt, that is short no matter how long the execution is. And those two are Starks. So in order for you to verify on chain, we have a Stark to Snark converter, and that is the Groth 16 kind of receipt, which is only 300 bytes, constant size no matter what you do. And then there's fake receipts, just for development, not for production. Now, what does a receipt say about the ZK VM? It's not only about program and output, it's actually about a straight transition about the ZK VM. So not only can you prove that some program produced an output, but you can also prove things about intermediate states of the VM as it executed your program. So this is what a receipt claim is. It's a claim about an execution. The pre-field is basically a digest of the state of the VM before execution. A post is a digest after execution. And there's an exit code for that transition. So you as a developer, you not only get to just write your program, you also get to specify which parts or during which phases is your program provable. So any proof needs to have an exit code, so you need to be explicit about that in your program. Also, the remainder is there's a digest about something called input. That's not the input you give to your program, that's an auxiliary input that you can use to label your proof. And the output is just a hash of the output that you have. So verifying proofs of successful execution is easy. You just have a one-liner with your program ID. But if you were proving unsuccessful executions. So if you're proving that the VM crashed for some reason while they're trying to prove, for example, due to a failed assertion or something went wrong, it's harder to shoot yourself on the foot, but you still are able to verify that. And if you're verifying on chain, we've deployed our verifier to the Ethereum mainnet, Arbitrum, Optimism, Base, and I believe some others that I don't have in mind right now. And it's as simple as calling into our verifier contract with your proof, the image ID, which is basically a digest of the program, and a hash of the output. And if that returns fine, then you should be okay. So where does this prover run? Well, you can run it in multiple places. Everything's out there. You can run the prover on our side on something called Bonsai, which is basically a cluster of GPUs that we manage to give you very fast proofs, because our proofs are fully parallelizable. So if you want more speed, you just throw more machines at it. You can run the prover that is supplied with the toolchain. So when you do install the RZUp utility, this just installs the toolchain prover on your machine. And you can also ship a prover with your application, fully embed the proving logic within your application so your end users don't have to worry about RZUp. And just make sure to enable GPU proving, because if you don't, you get slow proofs and the charts that I showed you are not valid. So also you might not want to do proving at all. If you're testing, you just enable an environment variable that uses fake receipts all the way. And for production, you might want to disable that, so you enable that feature. Right, so you need to get bytecode, you need to feed input to your prover, and you need to say what kind of receipt you need, right? And it's not only about actually providing bytecode and input, you actually define an entire environment for your program to be executed in. But compiling that bytecode is just a matter of wrapping your ZK program within the RISC Zero build system and just basically importing it within the methods crate. And then you get a nice constant variable that you can import that contains your bytecode and image ID. And to instantiate a prover with some specific options that tell it that you can prove intermediate states or what kind of receipt you want, just do that within the code as well. Here we're saying we need succinct receipts, and we're able to prove errors, so it's kind of harder. So you can actually create proofs for non-zero exit codes. But building bytecode within Cargo is not straightforward, so you might get different bytecode on different machines because Cargo is very sensitive to the build environment, but we also provide a way to get around that with containerization, so you can reproduce the exact same bytecode and get the exact same hash of the bytecode. Or you can skip builds altogether if you want fast compilation, but you need to build it at least once. Right, so I was saying you need to define an environment, and this environment actually is quite powerful. The simplest thing you can do is provide input to your program, right? Give it the data that it needs to do, but you can also provide other proofs to your program to use for verification. So your program might require, this is similar to recursion, so it's like verifying a proof within your program as it's being proven, but we call it composition because it's done outside the ZK VM to be much faster. Also, you can define custom callbacks for your program. So it might be that you need a non-deterministic hint for your program, like the square root of a number that gets computed outside your program, and then your program only verifies that this is indeed the square root. You also can specify in the environment the input label that I was mentioning, and you can also profile your program to see where the cycle hotspots are and optimize things. You can also pause your guest. This is important for games that actually want to pause the game, do the proof, and then continue later on when the user continues. And this explicitly creates separate sessions that you prove separately, and then you can automatically combine these. So how do you use this in the concept of blockchain? You will follow the co-processor model, where essentially on-chain contract requests some kind of operation to be proven, off-chain the proof is made, and then it's submitted on-chain again for verification to the contract, and the contract continues. For example, it is actually, for some DEXs, it's cheaper to compute the proof of how an order should be executed off-chain and then verify the proof on-chain than actually enact the full order on chain. This is currently used by Hashflow, which is a DeFi protocol, and Tally, which is a governance protocol. We also have a library called Steel for your ZK coprocessors if you want to verify the read on-chain state within your application. This takes care of preloading all the necessary inputs in terms of Merkle inclusion proofs, verifying all those, and then you can execute as many view calls against the Ethereum chain or any EVM chain as you want within your program. And we recently announced in our event a couple of days ago that we are building a prover network. If you're interested in taking part of that, do scan this QR code. This is the shilling segment of my talk. And I hope this has been a successful speedrun. If we have time for questions, I'm all yours.